So today, I'd like to talk about signatures. Actually, I guess that's here first. So signatures, what do you remember about RSA signatures? How do I sign something with RSA? I'd really like to talk about Bitcoin eventually, but we gotta. So I have a message. I want to tell everybody that I'm the only one that could actually make this message. So the trick generally, right, is I've got a public encryption exponent. So if somebody wants to send me a message, they could raise it to the E power, I raise it to the D power, and I get back to M. And this is all mod N. And this is because of, so this works because, I mean, E is some constant like 65.537. And then D we've carefully picked based on our knowledge of the factors of N to make this property work. So they can send me a secret message like that. How do I send them? Or how do I sign something and send it out to the world where anyone can decrypt it? Yeah, I just do these in opposite order. So this is the secret that only I can read, and this is this public statement that only I can make, right? So I can take any message, I can raise it to the D power. Anybody can raise it to the E power and say, oh yeah, that's the thing he claimed to say. And the trick is that no one else, unless they have D or knowledge of the factors, etc., can make the same signature. Right? So the idea is like for a currency transaction or something, you want to be able to say, I really gave you this money. Right? That's important. You don't want somebody else to be able to make up saying, oh yeah, Lawler gave me all his money. I don't know why, he just chose to, right? Right, so I want that to be I'm the only one that can actually make that statement. So signatures, validation are really important. Why does this work? Either one of these. I guess D to the E is E to the D. Why? Because multiplication is commutative, and that's good. Why is M to the E to the D equal to M?
Mod N.
Because it's all mod N.
Yeah.
Now, here's the really weird part. You can do this where N is prime. Now the problem is, if N is prime, then the relationship between E and D is actually really simple, that their product is the prime. Product is the prime minus 1. Product is the prime minus 1, I think. Yeah, so mod N. So the trick, the thing that makes this work is the fact that N is not a prime. N is the product of two primes, right? And we know what those primes are. So right, N is equal to P times Q. We know when I do multiplication inside this Bizarro group, it wraps around, and the trick is that this thing, right? So the whole point of the mod is that things are going to wrap around. It's going to wrap around back to 1. So there's this awesome theorem. Anybody remember Gauss's theorem?
I don't know which is Gauss's theorem.
Yeah.
I take a number. You're trying to forget it. You're saying.
No, I'm saying that Gauss has a lot of things.
He has a lot of things. Yeah. So I raise to some value any number, and I get 1 mod as soon as if I'm operating in a modular field. Right, there's some. I mean, what do I have to raise this thing to get 1?
0.
Well, 0 always works. Yeah. It turns out, right, because it's mod, it wraps around, right? So eventually this thing is going to wrap around. So it turns out this is the totient of N. You remember the totient function? Yeah, okay. Totient function. Right. So the trick is the totient tells you when when exponentiation finally wraps around again. Right. So what we pick is we pick basically, right, E times E equals 1 mod the totient, not mod N, mod the totient, meaning that right, we're going to basically be raising this thing to. Right. So makes sense. So what makes RSA work is knowing when this whole group wraps around in multiplication. This is how virtually every signature algorithm on the planet works, right? There's a bunch of different ones. Actually, we're going to be looking at one that's based on elliptic curves. The trick is knowing when this multiplication is going to wrap around, right? So I mean, what makes this hard is that it's tough to guess when, it's tough to guess what power I can raise something to get hit 1. I mean, if I multiply by 1 more, so I go M to the totient of n plus 1, that's going to be m, right? So if I set something equal to 1 mod the totient, then I'm good, right? Right. So I can have as many copies of the totient as I want up here, right? K times the totient, that's all good, right? This is the modular business, right? I can wrap around again and again. I'm just raising like 1 to the K, it doesn't matter, right? It's still the same thing. So imagine you're trying to solve this, right? I don't know what the totient value is. So what do? You just try some values, right? So this is where the mod is super duper important, right? So if I have I'm looking for a power that hits a constant, right? So if you look at the generalized version of this thing, say with floating point, right? So we're trying to find a power. So m to the a equals b. How hard is that?
Not hard.
That's really easy, right? What do you do here?
Log.
Take logs of both sides. Now you got a log. So the trick is that log works, right? So I can calculate a log m equals log b. Great. And the reason this works is because I raise m to the a power with real numbers. A gets bigger and bigger, b gets bigger and bigger, right? If m is greater than 1. So it's all easy, right? Very simple to figure out where am I close? No, I got to go way higher. Okay, I'm higher and higher. If I do this thing mod, it suddenly gets a heck of a lot harder. Why?
You can.
Well, I make a bigger and bigger, and this exponent gets bigger and bigger, and then it skips right over b, and you're like, well, shoot, what do I do now? You keep going, it wraps around, skips over b again, and you're like, when is it going to hit it?
Depending on the end, there might not actually be a solution to this, right?
It might not be possible to find some numbers.
Yeah.
Sure. Yeah. I mean, like, 2 to the what power gives you 4. It gives you 3. Any power of 2. There's no solution, right? It doesn't exist. You can keep wrapping around as many times as you want. Now, if I do that thing mod, 3 to the k, suddenly it's possible. Yeah. So right. So it's funny how this works. So the real trick is knowing when exponentially wraps around and exactly when it wraps around is what lets you solve these things. Okay. Any other questions about RSA? So we know totient, right? There's another technique that's similar to this, and it's just what's called DSA. Right, it's an RSA style thing. So you actually, again, you pick primes p and q. If you know primes p and q, you know what the totient is. You know when multiplication wraps around mod n. Use the same mod n, right? So you pick p and q exactly like RSA. You do mod n exactly like RSA. Then you compute all this crap. I can show you the crap. DSA. Now so I'm going to say this just enough to say I'm not going to talk about DSA. So, but the crap is not terribly important. So we do DSA, the digital signature algorithm, not the direct selling association or the firearms manufacturer. Let's see. So the calculation you do, it was patented for a while by a guy from the NSA. Let's see. So here's the signature process, right? I have a generator of the prime field. I compute. This is actually just Chinese remainder theorem for mod n. Let's see. So I'm basically calculating exponentials, wrapping around. I calculate some inverses. I end up with 2 numbers that are in the signature. I basically I plug those two. So I've made a signature. So the reason this works, it turns out, is because I know that's how I can do any of this stuff. And then I can verify the signature by doing more of the crap. It turns out DSA. You notice this is way more complicated than signing or verifying an RSA. Right? Like RSA, you just raise to a power once. That's it. Here, you start by raising to a power, and then you do some other stuff. That's a modular inverse operation. Right? That's there's a couple more multiplications. There's not that much happening in there, but it's enough. So basically, I run some stuff forward, I run some stuff backward, and DSA is actually kind of falling out of favor, it seems like. In other words, if you're going to use the PQ thing, people just use RSA because it's simpler to understand. There's fewer operations, which means there's fewer opportunities for timing attacks, et cetera, et cetera. And it's so as far as I can tell, if somebody comes with a technique that cracks RSA, it cracks DSA, right? And pretty much vice versa. So people are not really sure that DSA is actually worth any of the effort. Let's see. So that's a little frustrating because we would really like to have signature algorithms other than RSA because we know RSA might, somebody might come up with an efficient way to factor, in which case we're out of luck with RSA. So we want replacements. There is this one DSA laying around, but it's basically just, what's it?
Is it a different field, right?
So we switch fields actually, and I'm really amazed at seeing how these things tend to work. So it turns out you can implement DSA with an elliptic curve. So the result is called ECDSA, elliptic curve DSA. And then the trick is that instead of doing exponentiation, who remembers from before spring break the elliptic curves? What are our operations on elliptic curves? Okay.
Yeah,
We have point additions, right? So, like with elliptic curves, if I did like k dot g or something, g would be the generator point on the curve. If I start somewhere in the curve, k is an integer. Well, what does that mean? Well, it's not exponentiation. Actually, they usually call it exponentiation. So I do. So what I'm doing here is I'm walking along the curve, right? I'm walking along the curve. Usually they pick elliptic curves where they have what they call a large prime period. So in other words, if I keep elliptic curves a finite size curve, if I keep walking along a finite size curve, eventually I'm going to wrap around. It's guaranteed. Let's see. So if we look at like so we've got somewhere here is the order of the generator. So if you look up the details on any elliptic curve, they usually tell you all the stuff you need to know about it. So we have the P is the prime field that so this is the big prime, but all the arithmetic for calculating point addition of the curve is modulo that big prime. And then there's the order of the curve. And the order of the curve is if I keep multiplying G, eventually I'm going to reach 1 again, right? I'm going to reach the identity element. What's the identity element on an elliptic curve? It's not 1. 1's a multiplicative identity. It has different names like infinity or 0. In fact, those are the same. It's a little bit weird. It's like, so I get my elliptic curve. I calculate like a point intersection right between this point and this point, and it turns out, yeah, there is no other intersection. Right, it's the point at infinity. It's the identity element. It's the special magic thing. Actually, I've been reading there are other variants of these curves that don't have the special element, which I'm really tempted by. I like that idea. All your code, like so if we looked at the code that we did for like multiplying elliptic curves, doing elliptic curve arithmetic or something, you basically had to always check if I was doing addition and we were equal to infinity, we had to do something special, right? Like it's easy enough to add points to 0, right? If I'm adding additive identity, I kind of prefer the name 0 for it. So in other words, we're going to eventually hit the additive identity of 0. If we keep on adding, well, like k, so it turns out for any generator on any curve, there is some number where this thing is going to wrap around again to 0. If I keep going, n plus 1 times g, well, that's going to be g again, right? I've added another copy of g, and then back to where I started. Now, it's a little bit weird that the prime that defines all the arithmetic is 1 value, and the order of the curve is a different value. Ideally, they're both prime. That's kind of a then lots of stuff works nicely with that curve. So most of the curves that people have found, like the security group P2P6K1, it's both. It's got a prime modulus on the field. It has to for it to be a field, and it's got prime order, which is good because it means we can run lots of these same algorithms. So all it means by the order of multiplication is that n times the generator is equal to 0, right? Is equal to so it's we've wrapped around again. Now if I give you a random number like m and I multiply that by the generator, it's not going to be 0, but it might hit 0 on the way up to m if m is really big. I mean, so it's possible to hit this. There's an interesting fact here too. So I've walked down the curve away. I guess I should call it k. So I've calculated k times g, and so here I've got a new curve point. What happens if I multiply that by itself? I mean, I add it to itself n times. I mean, what is that?
It's not n times k.
I mean, well.
You can associate, can't you?
Yeah, so it turns out elliptic curve point multiplication is associative. So this is, I mean, it's equivalent to, I don't know what that.
Well, I mean, you can reorder it, right?
Yeah, and I mean, integer multiplication is commutative, right? So we can suddenly just, so that's equal to k times n. What's this equal to? Oh, n times g. That's 0, so this that's k times 0, it's still 0. That's weird. In other words, okay, what's the order of g? In other words, how many times do I have to add it to itself to reach 0? Well, it's n. What's the order of 2g? 0. It's the same order, and that doesn't feel right. The trick here is that we actually hit 0 once halfway through doing this. Right? This is actually the second time you've hit 0. And again, it's because this is equivalent to going around 2 times n g. That's also 0. I mean, so I bounce around the elliptic curve. I finally get back to 0. Take one more step. I'm back where I started. Right? So I do that again, and I'm back where I started. I mean, it's a finite curve. It's all wrapping around. Everything on the curve is essentially mod n. Right? That's the order. I don't know if that's visible at all. So, right. So I've got. So I know the order of the curve. This is something that's just published as an expression with every curve. So I can actually run virtually any algorithm that requires me to do like modular arithmetic that's going to wrap around eventually, and I can actually compute all of this stuff on the curve. So it turns out, I mean, you hardly have to change anything, right? You hardly have to change your definition of an elliptic curve. So if you say, well, how do I sign a message, right? And this is straight out of this is the DSA, non-elliptic curve version. Well, okay, what am I going to do? I generate a random message, random value k. I walk down the curve k, a distance of k. This whole mod business is just say, yeah, it's all mod the. I mean, it's implicitly mod the order of the curve. I calculate, oh, look at how deck is this. H of m is the hash I'm trying to sign. Hash thing. Let's see. R is the thing we just calculated. X is actually my secret key. So you have to calculate here a secret key. So there's your secret key. Here's your public key version of that. How do you calculate that? Well, you walk down the curve. This is the only thing you ever do. These algorithms, right? So pick a random number, walk down the curve that far. That's how you make your own private key, right? The private key is how far you walked. You remember that. The point you end up with on the curve is your public key. I can publish my public key. I keep my private key private so I can sign stuff. I can use that to sign stuff. I calculate this number. This whole thing actually. So let's see. K inverse. K is the sort of message secret key. X is my own secret key. R I just calculated. That's the hash. So the trick here is all this stuff is mod the order of the curve. This is all mod n, which is going to be important in a sec, right? So far we've, I mean, it's kind of hard to tell what the heck we've done. We've calculated these two values R and S, gibberish and gibberish. Supposedly they sign a message, right? In other words, if I give you R and S, my public key, the message, you can run some algorithm to actually verify that I did this. So here's the algorithm, and the algorithm is kind of uglier than it should be. So I calculate the multiplicative inverse of S This is actually exactly like this. How do I do multiplicative inverse? That sounds scary.
Find where another number equal to it, so it's just the other point.
Yeah. We are all mod n. N in this case is a prime. So I compute the old modular inverse. Anybody remember how do we calculate modular inverse?
No, it's the Euclid stuff.
Euclid's, the extended Euclidean algorithm will tell you that, yeah. I call a function, that's my, I mean, I usually have a hard time remembering. So we calculate modular inverse, right? I'm calculating modular inverse mod m of a value a. It's going to return a value I that's right to a times I equals 1 mod m. So here we're doing this all mod the size of the curve. So we have this this inverse process. There's another, the new hotness, and I may have to beg for real-time Python help to figure it out. There's a version that doesn't need the modular inverses, but not this one. So we calculate a modular inverse for S. We multiply the hash that we're trying to check by this modular inverse we just calculated. I don't know who the heck picked these letters. They seem really stupid to me. I call it S inverse. Right? So I just calculate S inverse once. I multiply that by the hash. I multiply R, which was just straight out of the signature, R by S inverse. And now I calculate, now this is the cool part. I walk down the curve by these two numbers, right? So I started the generator, walk down the curve. I started my public key, I walk down the curve by this other number. And add those two curve points together. And bam, I should be back to R. Why am I back to R? I don't know. We're here, right? So, so write this out in code, right? So here's it's not. There's not that much code to do here, right? So we gotta have a message hash somewhere. I guess, gosh, we picked a prime. I wonder if I can fit this all in lecture mode. I can hope. So we got a curve. We started a point on the curve. We have the order of the curve. We have the let's see. I generate a secret key, so I have a secret key. Is this the right one? This is the right one. Secret key. I walk down the curve that far, so I got my Q. Right. So we do the signing process, which is I have a random. So I get a signature, and so there's the hash I want to sign. It's treated just as an integer. This is the thing I'm messing up on the next one. So I've got an integer I want to sign. Well, first I need this is effectively a secret key for the message. I walk down the curve that far. Once I've done the curve that far, I pull out the x coordinate. That's r. I take that r, I multiply by my secret key. I add the message. This is all mod n. I now divide by k, which is the secret key for this message. So I've just signed this thing. There's rs, two big blocks of gibberish. I then do S inverse. Let's see, z. I take the hash. I multiply by S inverse. Take r, I multiply by S inverse. These are these u1 and u2s. I now walk down the curve. U1 from G, U2 from Q, add those together, that's supposed to be R. And you can print these out, and you can say, hey, it works. So if I'm signing I am a fish, so supposedly this will sign I as I am a fish. I always want to execute in Python 3. So I run this, so there's the hash I'm trying to sign, here's the RS, and I'll be darned, you run the magic, and you come out with the curve. The curve points I've wrapped around to get to the point where we're at the same spot. If you do it again, you get a different signature because we have a different. I mean, it's the same hash, and it's a different message secret key. And you can keep doing this, and it's it's relatively fast. It's 20 milliseconds, I guess. Now the real question is, why does that work? I mean, it's not obvious this should work at all, right? And in fact, if you mess this up, there's a million and one ways to mess this up. So let me show you several of the ways that I had messed this up. So if you don't read the part about S inverse, right? So now I just multiplied by S. It just fails. It's just like, well, shoot, C dot X, right, doesn't equal R at all.
You did it on both?
Just try like, I don't know what, nope, still does not equal, right? So there's R, and that's supposed to be equal to C dot X. But if you do this thing just right, using the recipe passed down from ancient times, then hey, it all works. Now, so the real question is, why should I be able to walk down the curve via these two different things and end up at the same place I started? The answer is how often it wraps around, right? So I'm going to end up at the same place if what algebraic thing is going to hold here. We're going to want, what are you going to, I mean, so where are we here? We're saying the curve point, C, this one that we're outputting. But it's if we've done this properly, it's basically equal to the generator to the K. But really, I mean, we calculate this as the generator to the U1, which I can't even see my own stuff there. Z over S, and it's your secret key Q times R over S. Well, okay. Unilluminating. What's Q? That's your secret key. How'd you calculate that? Well, that's G to some value. What G to your secret key, which I forget the notation. Your secret key is D, I guess. Yeah, D. When is this going to be equal to? So the question is, when is it going to be equal to G to the K? Right. R is G to the K. I walk down that far.
K equals dr plus dr.
Yeah. Okay. So now this is the trick. Mod the curve, right? So the curve is going to wrap around every time we do n. So the question is K equal to dr over S, Z over S? Is all look at that mod n?
I think the mod doesn't work right over logarithm. Like there's some weird.
Oh, right? In general, it doesn't work at all. The real trick here, right, is the curve. As I increment around the curve. Yeah. This is not like a general statement.
Yeah.
That would be a disaster. Okay. Why would this possibly be true? Well, we have two things that are divided by S. Let's simplify, see if we can make any progress there. So we have Z plus dr over S. Now, wait a sec. This should look familiar to you. Z plus dr. Hey. All right. That's some sort of progress, right? That's actually S, right? What is S? Well, S is that divided by what?
I guess the modular inverse of Kn.
Divided by K. In other words, we picked S to make this work, right? So Z plus dr over S, which is equal to Z plus dr over K. So we have 1 over K. That's K. Everything here we had to calculate all this stuff mod n, right? You notice it's mod n, mod n, mod n, mod n. N has to be a prime for divisions and stuff to be a field and for that stuff to work out. But so the real trick here is that we've actually just calculated, we've calculated something where we get back to where we started. We start with these two curve points and we walk down them. Now, so this is why a correct signature validates. I guess the harder question is why is it difficult for somebody else to fabricate this? I mean, what do they not know that means they can't sign stuff for me? Yeah, my secret key is the thing that I'm really trying to keep. I must keep that secret. So if they don't know D, they can't calculate that. They can validate it, right? Because I gave them R and S, which are enough for them to like take the. I mean, they can. And in fact, I gave them G to the D. That's my public key. Questions? Should we implement a different one? There's a simpler one that apparently all the cool kids are using. It was patented until 2008, which is why it's not really that popular. It's the Schnorr signature. There's no modular inverse, which sounds promising to me. Questions about ECDSA?
When do we get the magic,
And
How do we get the magic bit money?
That's what I was
That's
going
bit
to
money.
well, first,
yeah, I don't know how to get other people's magic bit money.
How long does this take?
Takes 18 milliseconds,
18.
maybe 20.
Per
To generate the keys, but to like.
No, that was
Generate
everything.
Every.
That was to generate myself a secret key, to sign a message, to verify the message. Yeah, that was all 20 milliseconds. Well, I don't know. Like so it depends on how many transactions you're validating, right? So like if you're say this would be a horrible implementation of Bitcoin. Say there's one server sitting in Satoshi Nakamura's basement or something that like everybody just like sends their messages to, and like his computer is like, okay, that's right. Then the problem is it takes 20 milliseconds to validate one transaction. He can validate 50 transactions per second. That's the limit on the size of Bitcoin. Right? So you don't. So performance of this thing is important. That there are, there's lots of. We're multiplying by G a lot here. In fact, like most of those multiplications are by G. If you start at the generator, you can make your multiplication way more efficient by like we saw from weeks ago. You pre-calculate all the powers of G, and this is what commercial implementations do. And you can save. I mean, there's at least like a factor of 2 or 3 speed up. You can, let's see, I am using my fancy, so I was actually kind of happy. I was able to just take my elliptic curve point class that we built last time. I'm even using the fancy one with the Z Jacobian stuff, and just drop it in there and start multiplying points, and hey, it actually all seemed to work out. Right? In other words, my signature checks in the end. Yeah. So we can in fact validate signatures. It seems like it's not quite as fast as it should be. Part of this is the modular inverse. Probably part of it is the the Python implementation of divide and mod are probably not super duper tuned. I know you can get a heck of a lot out of Montgomery reduction arithmetic, and yeah, so lots of stuff. So I don't know. I feel like this would make more sense probably if we build one from scratch. So I'm just gonna so let's do this. So I was looking at Schnorr and Pythonistas. I need help. Uh-oh. So the interesting part about Schnorr. So here's Schnorr. Schnorr is maybe a bad term for late afternoon class. Schnorr signature. Schnorr. Let's see. So here's how you sign. It's almost as easy as RSA, right? Walk down. So they all have this flavor, right? You pick a secret key for this particular operation you're doing. You walk down the curve that far. You compute the hash of the message you're trying to sign, ORed with the point. So this is actually kind of a cool thing. The curve points only end up going into hashes. You don't take export them. So this is where it's going wrong for me. The thing I love about this, you notice there's no divide there. It looks really similar to DSA otherwise. So I have a subtraction there. I have the same deal. I start at my curve point, I walk down to one signature, I take your public key, I walk down to the other element of the signature, add those together. That's all. I don't actually have to do any division or anything here for Schnorr. I like this. But to do it, I need to be able to calculate the hash of a message and a curve point. And how do I do that?
Curve point like curve point in terms of
Yeah, so I've got a get x, that's an integer, and I got an m, that's a string.
What is the hash expecting? Is it expecting big number, or is it expecting it in hex? Is it expecting it coded?
It's Python, you know that.
Well, that doesn't help you though.
Yeah.
At all. That means that's the point, right?
Well, so flexible types are like this, right? That, okay, so somewhere here I want to be able to take a hash.
But somewhere it's accepting a string. And what that string looks like is important. So
What it wants, I'm not giving it, which is bad.
that's the point, right? So what's it expecting? Is the question.
And I should probably write a function, except now I've forgotten how to do that. Okay, how do you write a function in Python?
Yeah.
Okay,
Maybe it's the same thing
this
as
should be easy.
Yeah, function, thingamajig, colon.
So hash this, and I'm going to take this parameters. This is going to be the message, and let's see the curve point. C. And I probably got to tab everything over. So my hope is I will just be able to return. So this will calculate the hash. So let's see. So this is going to be E is equal to hash this. So I'm going to take the message, take the curve point I just calculated. Now, and then this is the part that doesn't actually work. So I have an integer. I want to put it into a hash. I don't know what a hash takes. I don't know how to find out what a hash takes. Ben, feel free to jump in and save me here.
Oh, isn't it? I thought it just takes like whatever.
That's what I thought too, and I tried passing in, and this seemed to fail.
What is your hash? Is that the standard SHA-256?
That is the standard SHA-256.
I think
It's in hashlib. And it just says an object supporting the buffer API is required.
Actually, what does the second say?
Says very little about what the, yeah.
Oh, I'm looking at the hash lib here. You said
Yeah.
something else maybe?
Yeah, no, this is hashlib SHA-256.
I mean, it just totally takes a string, so maybe you need two strings.
I couldn't even take a string. If you pass a string, then it complains about like, oh, your string needs to be encoded. This is Python 3, so maybe it's pickier than other Pythons.
Oh, yeah, this is.
Yeah, Python 3 handles strings like completely differently than Python 2.
Yeah, they need to be encoded.
If we're putting a B before your layer, like
I figured it's not encoded, and that's okay.
Oh yeah, it is. Yeah, it is.
So my string is I'm fish. It's a string object. Any ideas?
What's a
Yeah, it needs to be a byte string.
So is it as simple as bytes?
string, common.
I tried constructed.
I think a B.
But
No,
no,
it just means that you want an actual string. That would be a much better. So I don't know how to do it.
That's fine.
If you put a U before the I am a fish.
But the string part is okay. The long
That part is okay? Okay. So you can call Unicode instead of string on the r.getx, and then you supply an encoding. So you can say like
string doesn't code.
so you do Unicode and then the string and then whatever the encoding is, ASCII or.
Int has no string.
Try byte. There's a function called byte.
Oh no, Unicode wrap Unicode around that r.getx. And then
There is no Unicode. You need to import Unicode. Import Unicode from Unicode. There is no Unicode.
You
Yeah.
want to try byte array?
This is embarrassing.
Just give it something.
See, somehow I thought this would be really easy. I must be missing something simple about Python. I'm sure I am. It's just no easier for. Why? Okay. Please, if you have to write documentation about any API, at the first Google hit, make sure there is a simple, complete example. And don't just like strip it down to say like, well, I assume you've like linked in the thingy and enabled the something or other. Just like give me everything you need. And if it's more than 1,000 lines, there's something wrong with your library. It claims import Unicode. Import Unicode data, maybe. I have no idea.
I thought there was a Unicode. I thought there was one.
You needed a space.
No, name Unicode is not.
I don't know, it's Unicode on data.
I don't know. That's frustrating. Sure, yeah, so this is
Why are we on
supposed.
Unicode? Because there's
I have no idea.
byte string?
I
It
have
seems like
no
there's a
idea.
function called byte. You give it a string and then you tell it what you.
I don't actually have a string. You know, at some point I knew how to convert it into a string. I've done it. It's actually in here.
You just do that string.
No. You
No.
just don't have a dot string. Yeah, it might be a dot string.
I have a double underscore string. I can convert the whole point to a string. I bet that works. So,
It's
I can take the whole
I
string.
think it's because the default representation of a string in Python 3 is a Unicode byte array.
Yeah.
So what if you do string and then str instead of string, and
I can
then
seriously not convert.
Rapid. Yeah.
like this? I sent it in the chat. str and then the text and then the encoding.
Object supporting buffer API. Oh, okay. Wait. I think we've done it. So I hash this. So I hash the message with the new location. Okay. We might be there. Signature valid. Woohoo! So okay, right. So show the trick. Thank you. Okay. Group effort. str. That's embarrassing. That was way easier than it should have been. Okay, so you convert to a string with str, not string. Got it. And that's ungoogleable because it's too short. So here's the magic. This is actually, I like this. Much more compressed magic. So we have calculated the hash of a message and a point, right? That's one half of this thing, right? Let's see, the E, that's the integer value of this hash. Let's see, I'm going to recalculate the point is the idea. So the hope is that R is going to end up in the same place. And why would this work? So I have, so this hopefully is the same exact deal. So we're doing the same thing. We have a G to the K. K is the secret string here. We've computed S. I guess I can't. Maybe the place to start is down here. So we do a G to the S. G to the S is G to the K minus XE. Let's see, and I multiply that by my secret string, which is G to the. Oh, I think I see where this is going. And beautiful. So there's my public key to the E. So again, that's G to the X. Let's see, and then we're going to raise it. So there's my public key. Raise that to the E. Why would this equal G to the K? Because minus XE plus XE. That's very simple and totally invisible on the projector, I'm sure. Hey, yeah, right. That makes sense. It was patented till 2008. Otherwise, I think this would be the standard. Like you would have elliptic curve Schnorr. It's just a thing everyone uses. Because it looks really simple, right? You can do, if you can do subtraction and multiplication, then you're pretty much there. I guess the other real questions are what are the holes in this? Let's say you didn't hear about this part about K being the message secret key. You just say K is another secret key. Okay, we will have that secret key. We will not change it. Sony did this for the PS3 apparently. They were using, let's see, so what I ended up with is you're going to have several different messages, right, that you're each going to get signed. They're all using the same K. So I end up with several S's that have the same K. And hey, look, right there, is the that's the secret key, the master Sony key that lets you sign new software to run on the PS3. So if you use the same K, then just the signature, I mean, you can ignore everything else. You don't have to do any curve stuff. This is now just modular arithmetic, right? You can calculate this part. I mean, subtraction gives it to you. I guess you have the secret key times E. I've forgotten what that E even was. Let's see. Oh, E is the hash. Yeah, so if I use the same key and I sign different things, so if I use the same secret key and the same message nonce, I'm in big trouble. Right? So there's two different values, right? These are going to differ by X. If I take like the GCD of two of these S values, mod Q, you're going to end up finding a multiple of X. You have a couple of 3 or 4 of them. In fact, you can find, so it turns out people on the internet managed to reconstruct Sony's private key because they had used the same K every time. There was another bug. This is actually kind of amazing. Apparently cell phone starts up. How much entropy is there in a starting up cell phone?
Very little.
Yeah. So it turns out they seeded their cryptographic, the accelerometers. You could imagine pulling information from several places that they didn't pull it. So there's actually a whole generation of Android devices where they had there was a Java crypto API that says like, get really good random numbers, where the system, like when it booted the Dalvik VM, the system had essentially no entropy. And it turns out that it wasn't actually. I mean, there were just a few bits of entropy, right? Like, you know, which of these things have started first. So, I mean, that's actually terrible, right? Because it means that all of the random numbers generated there were guessable. So this happened to Bitcoin. So they realized that, like, they looked in not virtually, every single Android wallet use the Java crypto API because it says in the documentation these are good cryptographic random numbers, and they look random, and they weren't. So people were actually able to steal all those bitcoins, which was really not good. So right, it's the same implementation details that we have with any of these things. When you call get random bits, these have to really be random. If you're ever getting the same K, so there's actually this interesting question. If we issue the same K, right? If we choose to pick the same K, I mean, normally you just throw away the K as soon as you're done doing the signature. It's more secure to just erase and overwrite the K, and you're done, right? You don't keep the Ks around because if somebody knows a K, then they could use that and any signature to figure out what your private key is. So it's better to just throw it away. Now here's a problem: if you can't use it twice, you can't throw it away, right? Or can you? So there's two contradictory requirements for K. One is you'd like to throw it away as soon as you're done signing, right? Because we input it in here and then we're done. The other is that you don't ever want to use the same K twice in a row. And if you have like a bad random number source, it would stink to actually have come up with the same K and not even realize it until somebody like
You can just
cleans out your accounts.
trust in random numbers and hope it's so vanishingly small.
What is the chance that I'm going to generate two Ks that are the same?
What's case?
The K is 256 bits.
Oh, it's like 0.
How like 0?
It's 1 over 2 to the 2 to the 6, which is right.
Okay, so the chance the K is like 6 is 1 over 2 to 36.
Yeah. But
The chance that these two Ks are identical is again 1 over 2 to 6. So how many Ks do I generate until there's going to be a collision?
That's the birthday problem.
Yeah, so we're actually back to the birthday problem. 2 to the 128th until we're expecting to find a collision, which is kind of scary. Yeah. So if you only generate like 2 to the 64th Ks, or like, I mean, how many financial transactions do you need on the planet, right? I mean, it's probably only a few billion per person lifetime, you'd think, right? There's only a few billion people, so it's really not, I mean, in cryptographic terms, that's a small number.
What do you care about throwing away the K? Side channel?
Oh, so if if I have like in the dumpster out behind the building, it's a printout of all the old Ks because we have to back up the database of all the old Ks.
What if it's in RAM?
Probably not. So here's a stupid thing, right? If you're going to explicitly check to see, like, have I used this K before? If so, oh no, error in cryptographic random generator detected. The problem is then we have to keep it around.
And then you know all the list of possible things you could do because you know what you cannot do.
Yeah. In fact, they can work their way through that list, and they can just like add those to the S's, or subtract them off the S's, and now they're halfway to knowing your. So you need to keep key secret, and you don't want to use it again.
22 trillion financial transactions a year is what it is.
It's a much bigger number than I
60
expected.
million a day.
Well, it's high frequency trading now, right?
Yeah.
So, I mean, in terms of like people actually buying something, like a person going to a store buying something, I suspect it's like several orders of magnitude much.
Yeah. Well, I mean, look at my bank account. Like the statement is 1 page, right, per month, and it's often like, yes, you bought gasoline and electricity.
Maybe we're not also
Pure and not tied to the mortal world like you are.
I bought an SSD this time, so it's yeah. I guess that doesn't show my bank account. The credit card statement has a lot more stuff. So, right. Yeah. So I don't know. So there's problems with handling all this stuff, and you can screw up any one of these and totally just break everything you're after. It's not the mathematics as usual, but the mathematics is not the problem. Yeah. So what do you do about these message nonces? So like Bruce Schneier says, don't worry about it. Right. Don't keep old ones because that's more dangerous than like use a good cryptographic random number generator. How do you validate your cryptographic random number generator is actually good? Boot your device, generate a key. Boot your device again, generate a key. Same key. You're in trouble.
Well, what if it's just a similar key, right?
Yeah, that's
You
the
gotta do it a
problem.
bunch of times.
Yeah, I don't know. You have to reboot your device 100 times a day.
You do it in a virtual machine.
So you
And-
just keep the first half of each key, so that way when you check it.
Excellent idea. Keep the hash of the keys. And then, right, it's tough to recover what the actual key was. You don't care what the key was. You just want to make sure whatever I get now is not the same as what I got before. There's in fact an idea that says you shouldn't be calculating. I mean, this doesn't really have to be random. If this is the nonce for the message, you can calculate it from the message. If I just say K is hash of the message, there's a problem with that. Well, I'm using it elsewhere down here.
Well, I mean,
And the big problem is anybody else knows the message can calculate the hash.
this is a signature algorithm, right? The entire point is that I get the message back.
Yeah, the message is public essentially. Right? I mean, you're going to give away the message. They have to actually take the message. I mean, the message is part of their verification process. Is this the message they used? So let's see. So I can't just hash the deterministic generation of the nonce is totally a thing. You don't just want to hash the message because everybody knows the message, which means everybody knows K, which means suddenly you just gave away your secret. So there's an argument that what you use is very simple. You use the one thing that nobody else knows, your secret key. If I hash the secret key, I get the same K every time. That's no good. If I hash the secret key and the message, now I'm fairly golden. You could put a counter in there if you want to extra paranoid. The date. Right. So so there's a fixed standard for this. Actually, on like if you want to generate a deterministic message nonce, you can. You can generate. I mean, again, Bruce Schneier says don't worry about it. Just generate a random number. I mean, if you generate two, honest to goodness, 2 to 6-bit random numbers, they're essentially never going to be the same. It'd be a huge, amazing achievement of searching of uselessness to say like I generated 2 independent 2 to 6-bit random numbers and they're identical.
That's the thing of the
It's sort of a proof that
right? Then you have to check that the entire KN graph.
You need
right?
2 to the 250, 2 to the 128 storage to implement the birthday problem, which
And then
is
once
with
you
random
do that,
access.
You just
Yeah.
search the whole KN graph. It's
Yeah,
insane.
yeah.
It's
So
not like a reasonable attack, I guess.
and it's it's probably not. Yeah. So deterministic. Some people say this should be deterministic. Does this part make sense? I really like this. I'm just going to teach Schnorr. Forget this DSA stuff with the dividing and the. There's only one mod. That's a beautiful thing. So you calculate the mod one time, right there. Everything else is just walk through. There you are. And any questions about this digital signatures? How do we get the Bitcoin? That's the. So we'll talk about how Bitcoin actually uses this to do transactions next time. Let's see, and what is due tonight? Project write-up. And again, if you're taking the graduate version of the class, this is a good chance to like practice writing graduate stuff.
It's so vague, like, hey, we expect you to write something graduate level.
Yeah.
Whatever that means.
Well, yeah. So scientific papers have a really idiomatic look to them, right? And to actually, I mean, if you don't know what that look is, I mean, I think I linked it from the course homepage. The other thing is it's scholar.google.com. This is sort of the search engine for scientific papers. So if you're interested, like in the Schnorr signature, there's going to be, say, the security of log signatures, and this is from a guy named Schnorr. That's a good sign. And you can download it from somesite.cn. That sounds legit. Let's see. So that unfortunately looks like the presentation. That is not the paper. So let's see. So here's .ru. And, I'm just downloading PDFs from. Yeah. Okay.
Yeah.
That's fine.
You know that
Let's see. Schnorr. Oh, good golly. Yeah. And that just downloaded it. So yeah, so I should be doing this all. So I can tell from the first step that this is a scientific paper. Why? Because it's formatted like a scientific paper. It uses the horrible ancient LaTeX font. So it's in Times, right? That's,
It says 1991.
yeah,
So
it's from
basically
991. I mean, feel free to make it look decent. That's I have no problem with that.
2 columns, because I didn't do that.
2-column would be cool. I personally prefer reading 2-column, frankly. But yeah, if it's a pain in the butt to do, then don't worry about it.
It's easy.
So you notice, I mean, in LaTeX it's easy, but LaTeX is hard.
Actually,
Yeah.
it's impossible.
So for example, like here's a citation to El Gamal. This is from 1985, and I know if I look at the bottom, it's going to say El Gamal somewhere in here. Now is that El? Yeah. Apparently it's a guy named El Gamal in 1985, and this is another big. Sort of cousin to RSA style stuff. So there's an extremely idiomatic set of stuff that pretty much every scientific paper has. Like it has an introduction, has a reference section at the end, right? And if you sort of just like can ignore this stuff, I can tell there's going to be like some charts or graphs, or actually math paper might be pseudocode. Okay, there it is. So this is going to say somewhere like how many multiplications did mine do? This is the new scheme, which will inevitably be called the Schnorr scheme. He doesn't have to even call it the Schnorr scheme. It's from Schnorr. Just say like, yeah, here's a thing. So that will be lost in obscurity, like most Waller techniques. So let's say so it's basically just saying like here's how this stuff works. The actual honest goodness performance numbers. So yeah, read the the Schnorr paper. Looks pretty interesting. Yes.
So my write-up was like a paragraph.
Are you taking the undergrad version? Yeah, so that's totally okay.
Yeah.
And it doesn't have to be this like. So here's the other. This actually frustrates me a little bit about scientific papers. They're usually really absurdly overly long, and they're extremely painful to read. I don't want to have to deal with that. I haven't even created the midterm for goodness sakes.
13 pages.
13 pages is fine. That's probably longer than I was hoping for, but
There's like 2 pages of graphs.
I'm good at skimming. So.
I'm shooting for like 5 in a month.
Like,
Yeah.
once he gets long enough that he just assumes the proper information.
I only spend.
If it's I am a fish on pages 15 through 30, I mean that's.
I like it long as not use action every day. So it's.
Yeah.
Yeah.
Yeah,
Oh.
format resubmitted.